Welcome back to the Biochemistry for Health Sciences channel. And this is Professor with my assistant Quirly. Last time we talked about electrolytes. Today we'll talk a little bit about calcium. Remember these videos right now that we are presenting. These are introductory videos, basically talking about a little bit about chemistry so that you can appreciate the medical relevance later. Okay, in future videos, we shall look at the ADME, absorption, distribution, metabolism, excretion, basically the physiology of these chemicals, as well as the clinical applications such as why do these chemicals increase in your bloodstream, for example, hypercalcemia, hypernatremia, hypercalcemia, and so on. Or why do these chemicals decrease in your blood? Hypocalcemia, hypokalemia, hyponatremia. Okay, so we'll leave that all for future videos, which you will appreciate once we accumulate sufficient background to understand the more complex issues related to electrolytes. So calcium is a routine test that is ordered in hospitals. The most common test is the total calcium, and you can see the value roughly in terms of milligrams per deciliter is about 10, or in terms of millimolar, that comes out to about 2.4 millimolar. Another calcium test that is actually better than total calcium is ionized or free calcium, and that's about 4 milligrams per deciliter, which comes out to about 1.2 or 1.1 to 1.3 millimolar. And you'll see in a few seconds why ionized calcium is better than total calcium, and that's basically because this is the one that is physiologically active. Okay, this is the active form of calcium, so therefore it will give you a better understanding of what's happening in the body. So there is about less than 2% of body weight as far as calcium is concerned. To understand the physiology of calcium and later the clinical usefulness and applications, we need to look at a little bit of chemistry of calcium. So we talked about the electrolytes. This is the electron configuration. These sodium has 1s2, 2s2, 2p6, 3s1. These are all the electrons that are located in these elements. And remember, chemistry is all about electrons. So in case of sodium ion, Na+, it has lost this electron. Okay, so it has lost this 3s1 electron, and therefore electron is negatively charged because it has lost an electron. So the sodium becomes a positive, gets a positive because it's lost a negative electron. And these species are called cations, sodium cation. Okay, similarly with potassium, here is the electronic configuration, has all the way to 4s1. Potassium ion or potassium cation loses the 4s1 and gets a positive charge. Chloride, you can see, is 3p5. If it gets an electron, if somebody gives chloride an electron, it becomes a chloride anion. And you see from 3p5, now he has an extra electron, 3p6. So that gives it a negative charge because electrons are negatively charged. Okay, and this chloride ion is negatively charged, while potassium and sodium, these are positively charged cations. Calcium has this 4s2. So when a calcium ion or calcium cation forms, these two electrons are given away so that it loses 2 electrons. So calcium will have a charge of +2. Okay, so the calcium ion is divalent, and that's a very important property of calcium with respect to its biological or physiological properties. So a salt like sodium chloride, you will have one sodium ion and one chloride ion. In calcium chloride, you have one calcium bound to two chloride, so that the net charge is 0. Okay, a negative and a positive cancels, two positive cancels, one negative and one negative here. So the salt basically the molecule has a charge of 0. So Cooley, what is the first thing that comes to your mind when you hear the word calcium? Halloween? Why Halloween? I see. That's quite true. That's skeleton, right? Where calcium is all about the skeleton. That's actually quite true. So most of your calcium, 99%, is in the bone, the skeletal part of the body, the skeleton, the bone and the teeth. And there the calcium is in the form of these inorganic chemicals such as hydroxyapatite, very complex formulas with all kinds of cations and anions such as phosphate and hydroxide. And then we also have in the teeth, we also have fluoroapatite. So yes, that's where most of your calcium is, 99%. Only 1%, less than about 1%, is outside the skeleton. Now in your blood, since we measure serum calcium, it's a routine test, you should remember that 45% of this calcium in your blood is bound to proteins. Okay, so this is the bound calcium. There's about 10% that is bound to anions such as phosphate, very strongly bound to phosphate, to citrate, to sulfate. Okay, so these are quite strongly bound calcium to other anions. And so these two species, let's call this bound calcium. Okay, bound calcium, either bound to proteins or bound to anions. Now, this bound calcium, some of this calcium can always dissociate, and there is what we call free calcium or ionized calcium, and that's about 45%. Okay, ionized calcium. This is the calcium that is physiologically active. That's why it's good to do the ionized calcium test rather than the total calcium. When you do total calcium, you're measuring all of this. When you're doing ionized calcium, you're actually measuring the one that is physiologically active. This is the one that will be taken up by the bone cells or by other cells and carry out its functions. An important thing to remember is calcium is an intracellular signal. We'll talk about cell signaling in future videos, but calcium is a very powerful and a very common signal in many different types of cells. Many different types of cells, which we'll come across in future videos. So basically in a cell that is not activated, or we see most of the calcium is either in the mitochondria, or the ER, endoplasmic reticulum. There is hardly any calcium in the cytoplasm. Okay, hardly any calcium in the cytoplasm. Of course, there'll be calcium outside the cell, like in your serum, but there's hardly any calcium in the mitochondria. Very insignificant amounts of calcium in the mitochondria. And this is because there are special proteins that pump the calcium into the mitochondria, or pump the calcium that comes out into the cytoplasm back into the ER and so on, or pumps it outside the cell. So this is a very important point to remember. Hardly any calcium in the cytoplasm of a resting cell. okay, of a resting cell. However, once a cell is stimulated, for example, if it's a nerve cell and an action potential arrives at a nerve cell, or something happens to an insulin secreting cell is activated, or the muscle cell is activated. So once a cell is activated, then one of the things we see that happens is the calcium concentration in the cytoplasm starts increasing. Okay, and that leads to all kinds of things happening in the cell. For example, exocytosis. If it's a neuron, it will start releasing neurotransmitters. By exocytosis, these vesicles in the cytoplasm will fuse with the plasma membrane vesicles, and the chemical inside these vesicles will be released. Okay, so neurons will release all kinds of neurotransmitters. The beta cell in the pancreas, when it's stimulated, the calcium increases, and the calcium stimulates exocytosis, and the vesicles containing insulin will fuse with the plasma membrane, and the insulin will be secreted out into the bloodstream. Okay, similarly in muscles, when they are stimulated, calcium levels increase, and that calcium then goes on to do other things that leads to activities such as muscle contraction. Okay, so calcium concentration, when it increases in the cytoplasm, it can cause cells to do all kinds of things. Besides being an intracellular signal, there are many proteins that require calcium. Okay, many proteins that require calcium, including there are several blood clotting factors that require calcium. So without calcium, as you know, blood will not clot, and that's the trick we use in the hospital when we collect a blood sample and we don't want it to clot. For example, when we want to prepare plasma, we don't want the blood to clot, then we simply add something like EDTA, which is a chemical that binds calcium very strongly, or citrate. Okay, EDTA or citrate will bind the calcium in our sample, and the calcium is not available for these blood clotting proteins, and the blood will not clot. So now this blood doesn't clot. When we centrifuge this blood, we will now get the plasma. The red blood cells and all the white blood cells will be at the bottom, and on the top will be the plasma. And in some cases, we use plasma for carrying out all kinds of lab tests. So how does this calcium work? Such a simple chemical, Ca2 plus cation. How does it do all this, stimulate exocytosis, and work as an intracellular signal and do all kinds of physiological or biological activities? Well, to understand that, we have to first appreciate that proteins carry out most of your cellular activities, and later in the future video we'll talk about proteins, and you'll see that proteins carry out most of the activities that cells do. Now, proteins have a certain shape, three-dimensional shape, okay? And the shape is what decides the function of the protein. So proteins work for cells because they have certain shapes, and these shapes can actually change. And that's how proteins work. Okay, just like shape is very important, not only at the molecular level, shape is important in everyday life. Okay, you have a knife, the knife works because it's sharp. The fork works because it has its prongs here, and the spoon works because of this part here. Okay, so you of course cannot use a knife to drink your soup, right? You can always try that, but that will be a very frustrating experience. So similarly, proteins, when they carry out a function, whatever the function is, it's because the fact that the protein has a certain shape, and the shape can also change. So that's the beauty about proteins. Okay, so that's how proteins work. So what does calcium do? Well, proteins, we'll see later, have got functional groups, such as positively charged amines or negatively charged carboxyls. And when the calcium increases in the cytoplasm, this calcium can come and bind the protein, and when it sits in the or binds the protein, you can see calcium is positively charged. It starts attracting the negative charges, and it starts repelling the positive charges, and that causes the protein shape to change. And when the protein shape changes, the properties of the protein change. Okay, for example, the protein might become more sticky. The solubility of the protein might go up or down and so on. Okay, and that also leads to changes in the activity of the protein. The protein function changes. It can become a better protein if it's an enzyme. It can become a better enzyme or a worse enzyme. Okay, so if it's a transport protein, it can work faster or it can work slower. That's how calcium affects cellular activities. So let's look at some of these examples. So here, calcium binding to the protein causes the shape to change, and that shape change can cause the function or the activity of the protein to change. So for example, clotting enzymes without calcium will not work, certain clotting enzymes such as factor 13, and then once the calcium binds, the clotting enzyme becomes active. Okay, the little A here for the activated form, and it starts working. Okay, calmodulin. Calmodulin is a protein that is very important in many cell types, such as smooth muscles. When calcium binds calmodulin, then the calmodulin protein changes shape, it becomes functional, it goes and affects other proteins, and eventually what happens is the actin myosin binds because of all these changes, and the muscle starts contracting. So smooth muscle starts contracting. Skeletal muscles, same thing in skeletal muscle contraction. Calcium binds the troponin complex, changes shape, the troponin changes shape. That leads to other changes in the cell. For example, another protein called tropomyosin is removed, and now suddenly the myosin binding sites are exposed on the actin filaments. Okay, the myosin binding sites, they are now exposed on the actin filaments, and now myosin can go and bind actin, and we have our skeletal muscle contraction. Okay, we'll talk about all these things later in future videos. This is just a quick summary of the versatility of calcium as an intracellular signal. So because of the positive charge of calcium, not only does the protein shape change to change the activity, the positive charge, you can see, can allow proteins to bind to membranes. Membranes contain chemicals such as phospholipids, which are negatively charged. So of course a negative protein and a negative membrane is not going to bind, but if the calcium is there, it will neutralize this negative and it will help the protein bind the membrane. One example, there are many examples of this, but one example is in clotting, the extrinsic clotting pathway. Factor 7 binding to the plasma membrane is actually helped by the presence of calcium. So calcium can not only change protein activity, allow protein binding to membranes. Calcium can also help proteins bind to other proteins. So for example, cadherin, these are proteins that are involved in joining cells together. Okay, cell adhesion. So calcium binding to this cadherin and this cadherin or another cell adhesion protein neutralizes the negative charges, and the cells can come together and bind. Another very important thing we see is in exocytosis. As we mentioned, exocytosis is how neurotransmitters are released or how insulin and other hormones are released and so on. So in exocytosis, calcium binds a certain protein, synaptogamine, and with the help of other proteins such as SNARE. Okay, exocytosis involves a lot of proteins, SNARE proteins, SM proteins, and so on. And eventually what happens is these SNARE proteins. So if this is a vesicle, here's your cell, the SNARE proteins on the, let me use a different color, the SNARE proteins here and the SNARE proteins here on the plasma membrane, when calcium binds, triggers the whole process, and suddenly you see cross-bridging. Bridges form between these vesicles and the plasma membrane, and then eventually the vesicles fuse with the plasma membrane, and whatever they have inside, like neurotransmitters or insulin, is released out into the extracellular space. Okay, so calcium, very simple divalent cation, can do a lot of things for cells by changing the protein activity, by allowing proteins to bind to membranes, or by allowing proteins to bind to other proteins. So just to summarize, ionized calcium is the active form found in your serum. It's the one that is used to make bone. Most of your calcium is in the bone. Less than 1% is outside the bone. Calcium is a very important intracellular signal. So basically, calcium affects proteins. Since proteins carry out most of the cellular activities, it's not surprising that calcium can be involved in neurotransmitter release, in insulin release, in contraction of muscles, in cells joining other cells, and in the process of blood clotting. Okay, so again, this is just an introductory video. We will talk about the ADME of calcium, the physiology of calcium, as well as the clinical applications such as hypercalcemia and hypocalcemia, and we'll systematically and logically look at why you get increased levels of calcium in your blood or decreased levels of calcium in your blood. That will be all done after we have accumulated sufficient background information. Cooley just reminded me that I mentioned a few times that there is no calcium in the mitochondria. So that was an error. What I meant was there's no calcium in the cytoplasm. Only when the cell is stimulated will the calcium increase in the cytoplasm. So I'm glad Cooley is awake, and he's a very, very good assistant. Okay, well, thank you very much for joining us. We will hopefully see you in the next video. So once again, this is the Biochemistry for Health Sciences channel, and this video is about an overview of calcium.